So this week we're going to be studying acceleration, but we can't really trust our finger to accelerate the cart uniformly down the track, so instead we've got this fan attached, and the fan is going to do the accelerating for us. We're going to study 4 different types of motion in this experiment, and I will show you all 4 of them in this video. But before you begin, as always, you want to level your track. We're going to level it this way first. Find the bubble that's going horizontal across the track. Grab the screws on the bottom of these legs. You twist them in the same direction at the same time. Then you also want to level the track in this direction. So put it upright like this. Then you'd want to go to one end of the track and again grab the screws on the bottoms of 2 of the legs and twist them at the same time in the same direction. So get your track nice and level, and then you put the cart back on it. So as I said, we're going to study 4 different types of motion. And in every case, what you'll do is you'll start the program running, turn on your fan, and then let the cart accelerate the way that's specified in the lab manual. The first one that we're going to study is we're going to start the cart from rest at 0, which in our case is actually the edge of the dead zone, so 15 centimeters away from the sensor. But we start the cart from rest at 0, and we let it accelerate in the positive direction down the track. So that looks like this. You'd start the program running, turn on your fan cart, and let it accelerate down the track. And that's the motion that you'd capture graphs of and then talk about in your report. And I will be showing you the program in a moment. So that's the first of the 4 motions that we're going to study. And the manual does ask you a set of questions for each of the motions. So now I'm going to take you over to the manual and talk about how you answer those questions for each of the 4 different cases that we'll study in this lab. Now for all 4 of the motions that you're going to be studying in this experiment, there's 4 questions they're going to ask you. So in the first one, they say, if the fan is moving in the way that's specified, describe how the position and velocity of the cart will change over time. So they're asking you to describe what the cart is going to do. So not the graphs, but the cart itself. In the second question, that's when they ask you to predict what you expect the graphs are going to look like for that motion. Now remember, in this experiment, we've got constant acceleration due to that fan. So when there's constant acceleration, we expect the position time graph to be a curved line. And for constant acceleration, we expect the velocity time graph to be a straight line. So you'd get in here and draw whatever you think is appropriate for your predictions. You'd also want to, down here at the bottom, discuss a little bit about what you're predicting. The third question asks you to then do the experiment and capture the motion with your computer program. So that's where you're going to capture the graphs and then screen capture them and paste them into your report. Before you do that, however, you're going to want to fit a straight line to your velocity time graph. And I'm going to show you how to do that in the program in a moment. The fourth question then asks you to talk about the similarities and differences between your predicted graphs and the ones you actually measured using the equipment. And to get full marks for this, you do need to talk about both the similarities and the differences. So for the differences, you might talk about the bumps and wiggles and weirdness of the data. And for the similarities, it's never enough to say that the graphs look the same. You need to be very specific about how they were the same. So you might say, well, they were both linear with a positive slope or a negative slope or a 0 slope. And the y-intercept was 0 or it was larger than 0. So stuff like that. So now we'll demonstrate the program that we're going to be using this week. So as usual, you go find the 1100 folder, open that up. And last week we used the velocity program. This week we're going to use the acceleration program. So double-click to open that up. And the first thing you'll notice is that we have 2 graphs now. We have a position time graph and a velocity time graph. And I'm going to demonstrate how these work now, so bear with me. It'll be a little bit noisy. But what I'm going to do is I'm going to click this collect button. I'll turn on the fan, and I'll let the cart accelerate down the track from rest, starting at the edge of the dead zone. So here's what it looks like. I click collect. Turn on the fan, let it accelerate, and I'll shut it off there. Now this area over here is the bounce back at the end of the track. We don't care about it at all. As expected, our position time graph of a constant acceleration looks like a curved line, and the velocity time graph, we can't really see what's going on there because we need to resize this. So remember from last week, the fastest way to resize your graph is to click on the number at the top or the bottom and just type in something else. And you can do this at the bottom as well. So that gives us a much better looking graph. And we can see that as expected, the velocity time graph for a constant acceleration looks like a straight line. There's a few bumps and wiggles, but this is roughly linear. So before you put these in your book, you'll want to fit a straight line to the velocity time graph. So how do you do that? Well, the first thing you do is highlight some data that looks pretty linear. You're welcome to avoid the bits that look a little bumpy and wiggly. Just choose an area that looks relatively linear. And then there's two ways to add the straight line fit to your graph. The first is you go up here to Analyze, Linear Fit, and it puts a straight line through your data that you selected, and it also gives you this fit box, which has the slope in it. Now, if you don't like your fit for any reason, you can click the little X to get rid of this, highlight New Data, whatever you think is reasonable. And then, as I said, there's two ways to fit a straight line through this. The first one is Analyze Linear Fit, but there's also a button up here at the top that will give you a linear fit. So I'll click the button, and again, it fits a straight line through my data and gives me this box that has the slope in it. And then you would screen capture these two graphs and paste them into your report. So now we're going to talk about the next three cases that you're going to study. So for all four cases, you're going to be answering those same questions in the manual. You'll describe the motion of the cart on the track, then you'll predict the graphs that you're going to see, then you'll actually capture those graphs on screen, paste them into your report, and finally, you'll talk about the similarities and differences between what you predicted you would see for the graphs and what you actually did see. So in the first case, we started the cart at rest from the edge of the dead zone, R0, and we let it accelerate in the positive direction. The second motion that we're going to study is we want the cart to have an initial velocity at 0. So how do we do that? Well, what we do is we move this cart right up close to the sensor, and that way, when he leaves the dead zone, he'll already have an initial velocity. So that's how we arrange that. So you would start your program running, turn on the fan, and start it from inside the dead zone, and then he's already got an initial velocity when he gets to here. So the third case we're going to study is a little trickier. So what we do for this one is we're going to move the cart to the end of the track, we'll start the program running, turn on the fan cart, and we'll give it a push back towards the sensor, so in this direction. So what will happen is that the fan cart will start moving in this direction, it'll slow down, decelerate, stop, turn around, and start accelerating in the positive direction again, back to this end of the track. So that looks like this. You'd start your program going, turn on the fan, give it a push towards the sensor, it'll slow down, stop, turn around, and accelerate back toward the far end of the track. And that's the motion that you want to get a graph of. Now I just want to show you a bit of weirdness in the data that you may or may not see on this third case. So, spoiler alert, this is roughly what your graphs are going to look like for this third case, where the cart turns itself around. The weird thing you might see is that the velocity time graph isn't quite linear. So what I mean is, if I highlight this data here and fit a straight line through it, it does fit the data well, but the slope up here doesn't match the slope down here. Likewise, if I highlight this data instead and fit a straight line through it, again, it fits the lower part of the data, but not the upper part of the data. So we've got two separate sections that are linear, rather than one completely linear graph. Now, the fan that we're using, it's supposed to give us constant acceleration, right? It's not getting stronger or weaker in the middle of the experiment. So if you see this kink in the data, this bend, there's something else causing it. It's not the fan. And again, this is something you're not supposed to see theoretically, but it is pretty common with our equipment. So if you do see this bend in the data, you and your group should talk about why you think that might be happening, because there is a question later in the manual that asks you about whether you saw this bend. So just to give you a little bit of a hint about why you might be seeing this, note that this bend in the data is happening right when the velocity goes to 0, so right at this horizontal line. So the velocity was equal to 0 when the cart changed direction, right? It slowed down, stopped for just a split second, and then continued on in the other direction. So the change in acceleration happened just as the cart changed direction. What could have caused that? It's not the fan, it's something else. Discuss it with your partners and try and figure it out. And again, your group may not see this, but if you do, highlight just half of the data, like this, fit a straight line to it, and then this is the graph that you would include in your report. And for our fourth motion, what we're going to do is we're going to take the cart, we're going to turn it around, and we're going to start it at this far end of the track and have it accelerate towards the sensor. Please catch it before it crashes into your sensor, but that's the motion you want to capture. So you'd start your program running, turn on the fan cart, let it accelerate towards the sensor, and just make sure you catch it before it crashes into it. Now, questions 5 and beyond are a little tricky, so I'm going to give you a few hints here. Not the answers, but just some hints on how to do these. So in question 5, they say, describe a real-world situation where
the acceleration is in the same direction as the direction of motion, or the acceleration is in the opposite direction as the direction of motion. So you might want to think about things like a cart accelerating or decelerating, or a ball being thrown up in the air, stuff like that. In question 6, they say, using the apparatus provided, suggest how we could produce an acceleration that was larger than the ones we measured, or an acceleration smaller than the ones measured. So what they're asking you to do is to think about ways that you could tweak the track, or the cart itself, or the fan itself, in order to change the acceleration that we measured. So there's more than one way to do this, and more than one right answer. In question 7, they're saying, describe a real-world situation where an object has a large acceleration but a small velocity, and a small acceleration but a large velocity. So again, think about real-world cases where this is true. So in the first one, a large acceleration but a small velocity, basically what you're trying to think up is a case where something is not moving fast yet, but it's going to because it has a large acceleration. So small velocity right now, but a large acceleration, which means it's going to have a different velocity very soon. And for the second one, a small acceleration but a large velocity, think about something that's moving fast right now, but its velocity isn't going to change much because the acceleration is not very large. In question 8, they say, using your data and fit lines, find a value for the acceleration of all 4 cases that we've studied. Now, by the time you get to this question, you've already got those numbers. You don't need to do any calculations here. You should be able to just go and look up the numbers and write them down here. Questions 9 and 10 are actually related to each other. So question 9 is, why were the first 3 measured accelerations that we studied all positive accelerations? And question 10 says, which acceleration magnitudes roughly agree with each other? And then discuss why they might have. So these are a little tricky, but one thing that helps you answer these 2 questions is to remember that we only had one fan. All the accelerations we measured came from the same device. So if you keep that in mind, it helps you answer these 2 questions. And finally, down here at the bottom, did you notice any differences in the acceleration magnitude related to the direction of motion? So as I hinted before, this has to do with that third case where the cart changed direction. Did you see that bend in the data when the cart turned around? If you did, you want to explain why that might have happened.